So we've got this layer of hydrogen on the surface, and as it gets thicker and thicker, the pressure gets higher and higher at the bottom, until eventually, because of the intense gravity, the pressure down here starts becoming comparable to that in the middle of the sun, at which point fusion will begin. But that's not going to make an explosion, surely. In our own sun, it's been fusing quite happily for several billion years without exploding. You might have thought that as all the gas rained down to form the sun in the beginning, it would have fusion, bang, the whole thing would explode. Why doesn't the sun explode?
Well, Paul, it's ultimately because the heat that's generated from the nuclear reactions, that temperature, also increases the pressure.
Okay.
So that central part of the star is going to want to expand a little bit when it gets hot, and when it does that, it counteracts gravity. And so rather than exploding, the whole thing puffs up a little bit, and then gravity pulls back a little bit, and you get this equilibrium where it's just able to burn at that rate where, you know, the thing doesn't explode and doesn't collapse.
So why doesn't that happen here? So why don't we get the fusion starts off, that puffs up the bottom layer, therefore dropping the pressure and the fusion rate, until it just equilibrates and just burns slowly and happily like a star?
Well, this is a very special place in the universe. This is the surface of a white dwarf, which we know is where the star is made of a degenerate gas. That is where essentially the quantum mechanical nature of the electrons mean you sort of push them as close as you can. And
So it's the uncertainty principle that's supplying the pressure and not the temperature.
that's right. And so that means that the temperature and the pressure are, which are normally related, like in the center of our sun, are not related here. They're sort of independent of each other.
So as the temperature goes up, because the fusion started, it gets hotter, but that means there's no more pressure, so it's not going to expand.
That's right. And so that means when you make something really hot, it's going to stay hot. And it's actually going to be able to affect its neighbors, which will also get hot and want to burn. So you would expect, at about the speed of sound, the entire layer of hydrogen to burn as a giant bomb.
Yep, so presumably a blob of gas falls through the accretionist lands on one place, and that's the straw that breaks the camel's back. Kind of fun if you knew you had a white dwarf that was just nearly ready to go, and you could go and drop one feather on the surface, and that would just push it over the crucial value, and then wham, it would light up in that place, and then a front would propagate around. You'd think very, very quickly. So you get something like this. There's an explosion and moves around the surface, and then bang, and blows it all out. In fact, these things, you'd expect it to happen in a fraction of a second. In fact, they take hours to peak in brightness, and no one's quite sure why that's the case. There's some various theories.
It's a bit of a
out there.
mystery, yeah.
Maybe it just takes a while for the blast wave to move around, or maybe it's generating power at the lower level, but it takes time to get up to the surface, or something like that.
Yes. Well, mysteries are good.
Yes, keep us in work. So, what's actually happening here? You're getting all these fusion taking place at the bottom level here. So you probably won't see that to begin with. But down there, it's going to generate lots of very highly radioactive isotopes. And these isotopes are also a lot of heat, and the heat's going to cause convection and carry it up to the top. And so you're getting all these isotopes dumped to the top, where they will decay and generate huge amounts of power. And so now the whole thing's going to glow very intensely. There's a huge amount of radiation coming out.
Right.
And it turns out that radiation can actually apply pressure. If you get intense enough radiation, it can actually push things around.
Right, because the photons are going to interact with, for example, the electrons and push on them. The electrons almost look like targets, right?
Okay, so let's see. Maybe that's going to be what's actually going to push this. We know there's a blast wave coming out. Maybe it's radiation pressure that can drive it. Let's do those calculations.